All right, so welcome everybody. My name is Claire Ratcliffe-Adams. I'm an education associate at the Space Science Institute. I am here today with Dylan Colony, our education specialist, and our special guest for today is Elena Sabbi, the deputy head of the Science Mission Office from the Space Telescope Science Institute. She's here to share with us what is going on with those images that we've seen from the James Webb Space Telescope. It's been so exciting to see all of those beautiful images come in. But today we're really going to dig into what work is being done using that data. Before we jump into things, I'm going to turn it over to Dylan to lead you through a quick icebreaker. This will be a poll question. So yeah, Dylan, explain the icebreaker, and then I will launch the poll and you should be able to interact directly with the poll.
All right, thanks everyone. So we thought, since we're going to be talking about what JWST is looking out there at the stationary orbit at L2, we would talk a little bit about what part of a star's life cycle do you feel like today? So we picked 4 of them. This is not, obviously all of them, but if you feel like maybe send a question with what you feel like something else, that's cool too, or you can answer one of these in the poll. So do you feel like a nebula? Are you maybe a little in process, a little all over the place, perhaps a little gassy? Are you a main sequence star? Are you stable, hospitable, just right, like the baby bear's chair? Are you a red giant? Are you cool, experienced, and maybe a little ready for quitting time? Or are you a black hole? Are you overloaded, feeling really dense and consuming anyone that gets too close? So go ahead and answer that with that poll question that Claire just shot up. I myself am feeling a little nebula-y today, but that might be the breakfast I had, who knows. But I look forward to seeing what all y'all say.
Dylan, I was feeling like a main sequence star until the chat function stopped working. So that threw me into a little bit of a nebula. I'm a little all over the place there, but for the most part, today's been a good day. I'm a main sequence star, and it's looking like we're getting some great answers coming through here in the poll. I'll give you guys about 5 more seconds to make your answer. All right, folks, looks like the answers have stopped coming in. So I'll share these results. We've got a good mix here of where we're all feeling today. Looks like the majority of us it's split between nebula, red giant, and black hole. And yeah, sad to say, only a few of us are feeling like a main sequence star.
It's okay. Hopefully we can all move from that nebula place into a main sequence place today. And I hope that the content we're covering today, talking about what's next for JWST, helps you at least feel a little bit more main sequence star-y in your STEM programming coming up.
Awesome. All right. Thank you all for participating in that. I am going to go ahead and stop sharing and turn it over to Elena to take us away on what she's doing with the Webb images.
Thank you very much. I hope you can see my screen properly. And so today we are going to start a journey. Just a second. We're going to start a journey to see what we can learn with Webb about how stars and planets are forming. And so if you're ready, I think we can all start together and just have a quick reminder of what is Webb, where it is working, and then we can start to look at the data that we got in the past few weeks. So just as a reminder, Webb is the result of a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. It was launched on December 25th from Kourou in South Guyana. And it was
Elena, I'm so sorry to interrupt. Yes. We're not seeing your screen shared.
Okay. Okay. So I'll start again. Just a second. And then we can go back. Can you see my screen now?
Yep, looks great. Thank you.
Yay. Okay, great. Okay, so welcome everybody. And today we are starting a journey together to figure out how stars and planets are forming using the Webb Space Telescope. This is a long journey that is going to be from our backyard to the early universe. And before we start, I would like to spend a few words about what is Webb, when was it launched, how did we launch it. So Webb is a collaboration between between NASA, the European Space Agency, and the Canadian Space Agency. Webb was launched from Kourou and has been launched from Kourou using the Ariane 5. The telescope was packed at the top of the rocket, and it was packed, folded in this very tight configuration that you can see in this image here, because the telescope is very big, and so it doesn't comfortably fit in any other way. These were the images that we were following on television the morning of December 25th. And as we were waiting for the telescope to unfold, we were carefully checking what Webb was doing using a camera that was on board of the telescope. At a certain point, the telescope opened its solar array here, and that was the last time that we had an image from the telescope. After that point, we had to follow every single operation that you are seeing in this animation, simply trusting the screen that we had in the control room. And there we were getting all information about the temperature and the electronics that were occurring in the telescope. So the animation was telling us that the telescope was unfolding, and we were trusting the little numbers that we were seeing in these very busy monitors. And we continued to monitor the telescope for 6 months as it was continuing. It was continuing to unfold. And then finally, after 1 month of operation, the telescope arrived in its final destination. That is the second Lagrange point in the orbit of the Earth. This is a point that connects the Earth to the Sun. It is opposite to the Sun. And as you can see in this plot, the telescope is following the Earth as it runs around the Sun. It is in an orbit that is much larger than the orbit of the Moon. And it is at 1 million miles away from the Earth. For comparison, the Sun is at about 100 million miles away from us. So the telescope is quite far away. It's much farther away than Hubble. Hubble is, don't remember where Hubble is. Hubble is at about 350 miles away from us. And so yeah, it's much farther away from than Hubble. Hubble is orbiting around the Earth. So every day, Hubble makes multiple passage on our head, while Webb is always fixed in the L2 position. So the reason why we made this very complicated launch, we sent the telescope so far away, it's because Webb is an infrared telescope, and it really doesn't like heat. The Earth and the Moon are quite hot for Webb, and as a result, they become very bright in the infrared. In fact, the side of Webb that is facing the stars and the other galaxies is at about 40 Kelvin, or if you prefer, minus 390 Fahrenheit, while the side of the Webb that is facing the Sun, it's at 400 Kelvin or 260 Fahrenheit. So there is almost 350 degrees difference between the side that is facing the Sun and the side that is facing the outside universe. And we are getting this very different excursion in temperature simply using these 5 layers of insulating material. We are dispersing the heat through the various layers, and this guarantees that the telescope is operating at the optimal temperature that allow us to see stars and galaxies. Otherwise, we would be completely blinded not only by the Sun, but also by the Earth and the Moon. Webb, as I said, is an infrared telescope. This means that it sees a very different light from what we can see from our eyes, with our eyes. The light that is coming from the sun, the other galaxies and other stars is much broader than what we can see with our eyes. It covers what is called the entire electromagnetic spectrum, and it ranges from the radio wavelengths up to the gamma, X-ray and gamma rays. These are all names that we find in our day-to-day life. They are ways to describe colors that we cannot see with our eyes. And these colors are very important because they give us information about phenomena that are associated with very different energies. You can see on top of these plot that there are a lot of wiggly thingy. These are a representation of the fact that the light moves as a wave, so it goes up and down. And for phenomena that have very high energies, these waves are very compact, very, very narrow, like we see, for example, in the gamma ray and in the X-ray. As we move toward phenomena that are less energetic, then we see that the space between the waves becomes broader. And when we are at the radio wavelengths, sometimes the separation can be of as big as the height of a skyscraper. So really, really big separation. In the when we are in the infrared or in the visible, we are talking about things that are of the size of the diameter of a hair, so much smaller separation between the various peaks and valleys. We want to see the universe in all its colors because we can understand much better how the universe works. And the colors that Webb can see are in the near and mid-infrared, which is this portion of the electromagnetic spectrum. Just to give you an idea of how the world looks like in the visible and in the infrared, this is a comparison of the same tree taken at just few seconds of distance apart. Let's take away the colors from the visible part, so it's the difference is more striking. You can see that the leaves and the grass are very bright, much brighter than they are in the optical image, and that is because chlorophyll is actually shining in the infrared. And on the contrary, the sky is extremely dark in this image. This is not an image taken at night. It's an image taken just a few minutes apart, but the sky is, the Earth's atmosphere is very, very good in blocking the infrared light. And that is another reason why we had to put Webb in space. Otherwise, we would not get the light from all the stars and galaxies. So we decided to look at the universe in the infrared because we have 4 key questions that we want to answer. The first one is see when the first galaxies lit up, how do they look like, when did they appear? The second one is to see how the galaxies evolved from the first structures that appear in the universe to what we see today in our backyard. We want also to better understand the life cycle of stars. Stars are fundamental for the development of life, and so we want to clearly understand how they evolve, how they modify the universe. And finally, of course, we want to explore the exosolar planet because this is a key way to understand our solar system, how did it form, and how life arrived on Earth. To answer these questions, we equipped Webb with 4 instruments that have very different characteristics, very different properties. The main imager, the telescope, the instrument that takes most of the images on Webb is NIRCam, that you can see in the center of the telescope focal plane. We have a twin imager or very similar imagers that is NIRISS. It operates it's overlap with NIRCam on a certain number of colors that it can see, but it also has very special ways of looking at exoplanets. Finally, we have one instrument that operates in the mid-infrared, so at redder color than NIRCam and NIRISS, and this is MIRI. And then we have one instrument that it takes only spectra. It doesn't take images. But spectra, I will show you later, are very, very important for astronomers to really understand the chemistry of the universe, how the various elements that we find on Earth, the oxygen, nitrogen, carbon, iron, arrived on Earth. And it is also very important to understand the properties of galaxies, the properties of stars, to understand where very interesting molecules, not only like water, but like methane or ammonia, are forming in the interstellar medium that is filling the galaxies. So with these 4 instruments, we want to really study the complexity of the universe. And to do that, we are actually taking advantage of special tools that are the filters. What you see here is the image of a planetary nebula. It is a beautiful image. It's all colorful. And this was an image taken by the Hubble Space Telescope. The colors that you see here, I'm sure now you know very well, they are not the real color of the images. They are the composition of multiple images added together. And what we do in particular is to slice the images in different components to highlight where the various elements are peaking. So for example, if we want to know where the helium is distributed in this image, we can use a filter that is associated with blue wavelengths, blue colors, and this will show us a region that is like this. It's dominated by stars. If you really, really squint, you can see that there is a little bit of nebulosity in the center. And then you can see that most of the structures that we see in the color images are absent in this distribution. However, if we, for example, check where the hydrogen gas is present, this is at green wavelengths. Sorry, this is the oxygen at green wavelengths, and we can see that most of the center of this nebula is filled with this with oxygen, while the hydrogen gas appears to be mostly segregated in the outside. There is quite some overlap between the oxygen and the hydrogen, and so this allows us to better understand this. Tricks allow us to better understand where an element is more dominant than another, better understand the contribution of the various components. But of course, as you can see from the scheme down here, we are also losing a lot of information. So we don't know what happens in all these other ranges of colors. To gather that information, instead of looking at an image, we can put a prism or a slit in front of our source and collect what is called the spectrum. So what we do is to take all the light that is coming from that source, organize it in order of increasing energy from red to blue in the optical, and we can do the same in the infrared, although we are using different names because we see different colors there. And when we do that, we see that in addition to what looks like a rainbow, we have a series of dark lines that correspond to the fact that in these materials, there are also a lot of chemical elements that are stealing a little bit of light, and they are causing the spectrum to become darker. If you collapse the spectrum, we can see how deep these lines are, and by comparing how deep a line is compared to another, we can figure out how abundant an element is compared to another. So for example, we can say how much oxygen there is with respect of iron or with respect of hydrogen. We can also determine what is the gravity, the surface gravity of a star by looking at how broad these lines are. We can determine the temperature of a star by looking at where the peak of the spectrum is located. So basically, really, a spectrum gives us the full identity chart of a star. It really unlocks all the properties that a star or a galaxy have. And for this reason, a spectrum is extremely important for astronomers because really give us all the information that we can desire. And so if we say that an image is more than 1,000 words, for astronomers, often a spectrum is more than 1,000 images. After this introduction of the tools that we use usually to understand astronomy, I think that it's important to start to figure out what is the, to start to dive into the 4 themes that Webb wants to explore. And so we can start with the origin of stars and galaxies. And also we can spend a couple of words figuring out why do we want to look in the infrared to understand this concept. What you see here is an image of the deep field that was observed by Webb. It was the first image that Webb released. However, this is how it looks like when we look at this region with Hubble. So I just want for you to remember what we can see with Hubble and then compare it later with what we can see with Webb. Webb is extremely important in the infrared is extremely important to understand the very distant universe, because the light, as I said before, behaves like a wave. And so it is subject to the Doppler effect exactly as the sound is. So if you are the observer here and you have a car approaching and the car is making noise, if the car is coming toward you, the waves that are emitted by the sounds get compressed, and so the sound appears very compact. If the car moves away from you, the wave gets stretched, they are pulled, and so the sound gets prolonged. And this is what we can see in this little animation. We experience this in our day-to-day life, but we can also experience this with when we look at the universe. So this is a schematic representation of how the universe has been expanding following the Big Bang. As a consequence of the expansion, the separation between the galaxies is increasing. And so the light that initially was very blue because it was emitted by hot stars, it was very high energy light, progressively it stretches as it approaches us and it moves to a redder color. So if we look in the blue filters, we cannot see this light because the color is completely out of the filters that we are using. We have to use redder filter and possibly infrared telescopes. So this was the image that was released. It was the first image released for Webb. It was presented by President John Biden, and it shows a cluster of galaxies that are magnifying the light that comes from galaxies that are much farther away. We call this phenomenon the gravitational lens because the matter that is in the center of the cluster is acting as a lens, and it is increasing the luminosity of the stars that are in the background. And at the same time, it is also distorting their shape. And this is why we see these arches. This is how the image looks like when we look at this region with NIRCam, that is the camera that operates in the near infrared. And this is the same region when we look at it with MIRI. MIRI is less sensitive to the light of the stars. It looks at much cooler sources. But on the other hand, it's very, very sensitive, for example, to dust. And so the stars that are very bright in this image are much fainter in the mid-infrared image. And at the same time, we see that galaxies that appear having similar colors in the NIRCam image, like here, have quite different colors in MIRI, because, for example, one galaxy contains much more dust, and so it is redder than the other one. Now, if we want to explore in detail what is in this image, we see that there are a series of sources that have these spikes on top. These are all stars, and only stars shows these structures. All extended objects should have these structures, but then it gets diluted. We can appreciate these structures only in the stars with Webb. And the number of spikes that we see in this image is the signatures of Webb. If you look at Hubble, for example, there are only 4 spikes. In this image, in addition to the stars that are all in the foreground, they're all stars that are in our galaxies, we can see that there is a group of galaxies here that are all compact. They are sort of wrapped in these nebulosities. These are the central clusters that is acting as a lens. These galaxies are all bound together by gravity, and this system is so rich in mass that is actually pulling toward itself the light that is coming from the background and toward us. So instead of coming on a straight line, it's bended toward the cluster. This is why we can see all these background galaxies that have this distorted shape. They look like arches. And the arches are also telling us where the center of the cluster is, the center of mass is. The other effect, as I said, is that this lens, it also makes the galaxies brighter. And so we can see systems that are quite faint becoming more easily accessible to us. There are multiple clusters in these regions, and some of these clusters, this was beautiful for us to see. Some of these galaxies have a series of little dots on top. These are all regions of massive star formation that are basically the younger counterpart of the massive globular clusters that we can see in our galaxies. So if you think of Omega Centauri 47 Tucanae, these are basically how they looked like when our galaxy was much younger. And we can see example of this system all over the place. The image was taken in multiple filters, and it allowed us to have an idea of how far the galaxies are, and also to create a sort of compilation of closer to farther galaxies. However, this measurement is quite uncertain because we only we have a broad range of colors that we can get inside a filter. If we want to better characterize the properties of the galaxies, what we can do is to use spectra. And this is what we are doing, for example, in this small region here, where we, instead of looking at the cluster of galaxies with an imager, we use it through the spectra that are collected by NIRIS using GRISM. Basically, all the image here is, all the light comes through a GRISM. And as a result, all the light is ordered in its colors. What you can see here is that in some cases, the spectra end up overlapping to each other. And this creates a little bit of confusion for astronomers because it becomes very difficult to separate the contribution of one source to another. But we can also, for example, study the properties of these two arches that we see in this image. And when we do that, we see that the spectra of these two arches are perfectly identical and that the two systems are exactly at the same distance. And we can infer that by the position of the spectral line that move because of the Doppler effect from the position that they would have in our laboratories to the position that is determined by the expansion of the universe, how fast these galaxies are moving away from us. So as I say, these two spectra are identical, and this means that these two arches are actually the image distorted by the gravitational lens that we have here at the center in these two arches. Now, these spectra are very compact, and so again, they don't give us all the information that we would like to gather for these systems. We are quite greedy. We want to know as much as possible from the galaxies that we are seeing in this very distant universe. And so what we can do is to mask most of the light that is coming from all these sources and just focus our attention on some of the most interesting galaxies that are in this image. And we can do that using another instrument that is on board of Webb. This instrument is called NIRSpec, and it is equipped with 250,000 of individually independent microshutter little doors that you can open and close. So we can select exactly which galaxy we want to study by simply deciding to open a microshutter instead of another. In doing so, we are getting extremely clean spectra, and we can also get spectra that have much more resolution. In this slide here, we are showing the spectra of four galaxies that have different distances. We suspected that these galaxies had different distances based on their properties on the images, how the luminosity changed in the filters. And then when we look at these lines of hydrogen and oxygen, we see that the same lines are moving toward redder colors, as we expect with the expansion of the universe for objects that are moving farther away from us. And so the first galaxy here is at 11.3 billion years away from us, so a couple of billion years after the Big Bang, while this galaxy here is at 3.1 billion years from us, so 700 million years after the Big Bang, so much younger system. Now, when you look at this spectra, you can see that we have much more resolution. And so the line that I was showing you before of the oxygen in the low resolution spectra was just one single line. We see now that is a composition of two separate lines. And then when you look in this part of the spectrum, you can see that there are many more lines. And these are lines of multiple, of different species. We have hydrogen, but also we have oxygen, and we have neon. And so all these lines are giving us an information about the chemical composition of the galaxies that we are looking at. Now, when the universe started, it was made only of hydrogen and helium. It was a very simple composition. All these other elements that we see now in galaxies were formed in the interior of stars, and they started to appear we started to populate the universe after the stars exploded as supernova. So the fact that we can see these elements in this galaxy is telling us that already 700 million years after the Big Bang, we had a series of supernova explosions that have enriched the gas of these elements that before were not present in the universe. And in particular, we were extremely excited of seeing this little line of oxygen here. This is a line that we use in the local universe to characterize the abundance of oxygen in nearby galaxies. It's a tracer of the chemical evolution of galaxies in our nearby universe. And the fact that we can see this line so far, at such a high redshift, such a large distance, means that we can really trace the evolution of our universe in a consistent way across all its evolution. And this is very exciting for us. Now, in addition to see when the first galaxies appeared and how did they look, how big they were, we also want to see how they changed over time. So we want to study their evolution as the universe evolved. When we look at very deep fields, we see that the galaxy, we can see very distant galaxies, and they usually are like small dots. They are compact, they don't have many structures. But then as we move at intermediate distance, we see that the majority of the galaxies are irregulars. They have a lot of star formation and they are very spotty. And then in the nearby universe, the majority of the galaxies appears like spirals or giant ellipticals. So we really want to see how this evolution progress and when the various population becomes more important. And this is another area where the superb resolution and sensitivity of Webb is going to provide us a lot of information. And just to give you an example, this is the quintet, the Stefan quintet. It's a group of galaxies that are interacting. This galaxy here is not actually part of the quintet, is a foreground galaxy, so it's much closer to us. But these are the galaxies that are interacting. You can see that there are two galaxies here that are connected by this beautiful dust lane, and then there is another big galaxy that is extremely distorted, and in its center there is a gigantic black hole that is right now collecting a huge amount of material, and as a result the black hole, it becomes extremely bright, and we call this type of object active galactic nuclei, or AGN. Now with NIRCam and MIRI, we can appreciate all the infrastructures. We can see where the various galaxies are. With MIRI in particular, we can see where all the dust and all the complex molecules are distributed. You can see in this image how bright the nucleus of this galaxy, where there is the massive black holes, appears. It almost looks like an extremely bright stars, but it is actually the core of the galaxy. And there are all these beautiful arches of material that are orbiting, funneling around the black hole. In addition to looking at this image, at this region with images, we can also look at this image with spectra, and we can use our spectra in a very special way. We can order our spectra on a grid and put each spectrum one side by side to the other. And in doing that, we can recreate a map of every point of the chemical variation of each point. In doing so, what we can do is basically to recreate an image, but each pixel of this image, that is usually called speckles, contains complete information of the chemical composition of that region. In this particular example here, we subtracted the contribution of the bright AGN, and that allowed us to highlight how from the AGN there are two powerful jets of material that are ejected from the center of the black hole back from the surface of the black hole back to space. And the bright part that we see here is where the jet is hitting against the gas and dust that are filling the galaxy. And as a result, the gas becomes extremely bright and it starts to shine. Now, as I said, every point of this image is actually a spectrum. And so we can extract the spectrum into regions, one, for example, associated to the jet, and see its properties and compare it to how the spectrum that is associated to the region where the AGN is located. And we can see that in this case, there is this very broad band of, this band is much fainter than in this region. Here the spectrum is flat, here we have a very different shape. This region here is where we have a thick disk of dust that is orbiting around the black hole, and it is falling on the black hole. And this is a very dense region where there is a lot of friction and there are a lot of silicates and molecular hydrogen. On the other hand, in the jet, where the material is expelled, we have a lot of energy, and we see that there is a lot of excited gas. And this is why we have all these very narrow and bright lines in the jet. We can slice the spectrum at different colors, and these allow us to see where the various elements are distributed. But also, we can measure the position of the lines and compare it to their position on Earth. And in doing that, we can see that sometimes these lines are moving toward red colors or away from us. And in other cases, they are moving toward blue colors or toward us. So in this way, we can see the relative velocity of the gas that is expelled from the black hole, how fast it moves. It moves at 400 kilometers per second difference peak to peak. So it's really a very powerful and energetic event that can create this beautiful jet. And we can see exactly how the gas is moving around the black hole. And I think that this is really, really amazing if you think that we can do this. Now, this is what happened in distant galaxies, but also we can use Webb to really trace what's going on in nearby galaxies. In our own galaxies or nearby galaxies, and see how the stars are changing. This is a planetary nebula. It was studied by Hubble, and you can see that there is the main stars here, and here there is the faint companion that is associated to this nebula. We want to look at star forming region in the infrared, because usually stars form in very dusty environments that are hiding most of the light that we can see. In this region, for example, that was one of the Hubble anniversary images, the stars and its neighbors were completely protected in their dusty cocoon as they were growing, and we were missing most of the information when we were looking at the region in the optical. And then in the infrared, we can see that there is this multitude of sources that we were not able to see. This is a Hubble image. Hubble has some infrared capabilities, but also you can see that not all the light can go through the dust, that Hubble is not powerful enough to penetrate through the thicker layer of dust. And for this, we need to go through Webb. And this is, so really we want to go through this thickest walls of dust and see where the stars are forming now. In particular, I would like to show you how Webb can give us information about stars and how they form. This is probably one of the most iconic images that Hubble ever took, is the pillar of creation in the Eagle Nebula. And these are huge pillars of dust and gas that are basically as high as the diameter of our solar system. At the top of these regions, there are stars that are forming right now. And when you look in the infrared, you only have to take my word for that, because you cannot see the stars. But as soon as you move to the near infrared, with, for example, the wide field camera 3 channel, you can see that the stars start to appear at the top of these pillars. Again, you can see the multitude of stars that were blocked by all the dust and that is protecting the star-forming region. And again, you can see that not all the dust becomes transparent for Hubble. If you move to the mid-infrared, that is where MIRI operates, all the stars disappear. And what you can see is that the dust that in the optical was a sort of annoyance, in the mid-infrared becomes really the protagonist of our image. It's what shines. And also you can see that in this image, there are slight, small variation in colors because the dust can be very colorful if you look it in the right way. This is a Spitzer image, so it has much lower resolution than what Webb can do. With Webb, we will be able to really appreciate all the details of the various structures that we see in this image. And also, we will be able to take spectra and really start to see where these complex molecules like ammonia, methanol, methane, carbon monoxide, carbon dioxide are forming. These are really the building blocks that we need, for example, to put together the amino acids that are responsible, that are necessary for the development of life. And so clearly, we are all waiting to be able to look at where these ice, where all this ice is distributed and how it moves around in space. So just to show you the capabilities that Webb has in terms of star-forming regions, this is NGC 3324. It's a huge bubbles that encircle a relatively old region of star formation. Here there is the central cluster. This region is huge, and so it would take forever to map it at the resolution of Webb. At the moment, we only looked at this small area here that looks a little bit like a nose. And this is how the same region looks like with Webb. Now, you've probably seen the region this way. It looks like a beautiful skyline with the mountains that are in front of this beautiful starlight sky. But for astronomers, this region is amazingly interesting because, for example, we see that the distant bright stars that are up in the center of the bubble, and we cannot see in this image, are disrupting all the dust that is at the edge of the bubble. And we have evidence of this phenomenon. For example, here, where we see that there is all this hazy nebulosity. These are dust grains that have been evaporated, and they really create this foggy environment. We have also see that there are regions where stars are forming right now, like in this point here. There is a little cluster of stars here, and as stars are forming, they accrete material from a disk, and then to stabilize and their energy, they tend to create big jets, similar to what we saw in the black hole. They also create jet and expel part of the material. And here we have this example of this beautiful jet that is shown here. And we have another example of jets here. This is one of the jets. And I think that the most interesting one for me is this little guy here, where we see that the jet has a sort of a twist. And that is because what we are seeing there is a binary system that is forming right now. So the two stars are orbiting one around the other. And similar to what we see, for example, in the garden when we are watering plants with the spinning system, the water is also, and the water is doing this movement. The gas and dust that are on the jet are doing exactly the same bending movement. So this is the demonstration that there is not a single star, but a binary star that is forming. One image that was not released in the press was this one. This is how the same region looks like when we look at it with just MIRI. So we are focusing our attention on the dust. Almost all the stars are gone, and that is because in the mid-infrared we see very cold objects that are very cold, objects that don't have much energy. So this is the perfect wavelength to study the properties of the dust, but it is also the perfect wavelength to highlight where young stars that are not burning hydrogen yet are forming. They are still growing. They don't have enough energy yet to burn hydrogen in their core. And so they are cold enough that we can see them perfectly well in the mid-infrared. We can see that there is, for example, a line of stars that are forming here at the edge of the nebula, where the gas is compressed by the radiation. There is the little cluster that I showed you before with the two jets that we were seeing in the NIRCam image. And this is how NIRCam and MIRI combined look like, and shows all the power of Webb. Here there is, again, the little binary stars that I was showing before, and here it's the line of stars. You can see that they have very different colors. These are the most embedded one, very young stars, still completely covering the mostly covering in their dust shine, and they're still growing. And this is a star that has foreground stars already emerged from the cocoon, and so it looks very blue. If Webb gives us information about how stars form, it is also extremely powerful in showing us the last stages of stellar evolution. This is the Planetary Nebula, a star that is approaching its final evolution. It's approaching its death. This is the image with NIRCam, and you can see that the star has already lost multiple part of its outer layer in a series of multiple expansion and contraction that are responsible for all these beautiful layers. You also see that it looks like the center of symmetry of the system is changing. The first explosion maybe it was aligned in this direction, and now it seems to be aligned. The most recent one was aligned in this other direction. And that is because this is a binary system, and so we have a change in the rotational axis. The companion that was barely visible in the Hubble image is almost completely hidden in the NIRCam image, because there is the diffraction spike that is aligned to the star. That was an accident, it wasn't planned. But then I would like for you to notice how bright the companion becomes as we move in the mid-infrared. And it is almost as bright as the primary star. And that is because the companion is completely wrapped in a dusty cocoon. It's very, very cold, and it is very, very dusty. And so it becomes very, very bright when we look at it in the mid-infrared. To move toward the end, my time is running out, I'm sorry. I would like to spend a couple of words on how are we going to use Webb to study the exosolar planet. We know that when stars form, they are surrounded by dusty disks. We've seen this, for example, in the Orion Nebula using Hubble, and then we've seen in other cases, both from the ground and from space. This is another image with Hubble. In this case, we were able not only to see the disk that is seen at John in this case, but sometimes we had also evidence of comets that were going to run toward the stars. So we can get a lot of information by studying the disks of young stars and that are still forming. And we're using with ALMA, we were also able to demonstrate how these disks evolve, and they develop rings as the star grows and mature. And we see with ALMA that these rings are carved by the presence of little rocks that are tumbling around the disks, and they are growing material. And these little rocks are the seeds that will become the planets that we find in the exosolar, in the various planetary systems. So what we want to do is to see how the chemical compositions of these disk changes as the disk ages. And that is because in the outer parts of the disk that are the coldest parts, the parts that are far away from the stars, is where we know that ice of methane, water, ammonia are forming. They are coating the dust grains. And then sometimes these coated grains can migrate into the inner part of the disk in the form of comets and asteroids, and they can impact the young rocky planets that we find in the inner part of the system, of the various solar systems. We think that this is how water arrived on Earth, and we want to prove that this hypothesis is correct. We want to see how long it takes for this transfer of molecules to occur. And to do that, we need to study disks that are different, that are in different evolutionary phases. We are going to do that using spectra, and these are a collection of the complex molecule that, for example, we can see with Webb in the various disks. In addition, we want also to study planets that are already formed and see how their atmosphere and surface changes as they orbit around the stars. As they orbit around their stars, they are showing us different phases, the different sides of their phase. And so by looking at how they are illuminated, how their temperature changes, how their albedo changes, we can get information on the chemical composition of both their crust, if their atmosphere is thin, or their atmosphere if instead it's thick. Oops, I didn't know that there was an animation, sorry. So what we are going to do is to look at various planets as they transit around their star. What you see here, it's real data. It's the first transit that we observed with Webb, and it's an extremely precise measurement. It's really, it looks like a simulation because there is almost no error bar, and that is because Webb is so precise, so sensitive. But in addition at looking at the curves of the eclipse, we can actually see how the atmosphere still lights from the star, the atmosphere of the planet still lights from the star, and use spectra to try to characterize the properties of the atmosphere. We did this experiment with the planets that I showed you before. This was a planet that was already observed with Hubble, and we suspected that there was water in the atmosphere of that planet. However, the measurements were not conclusive because there were too many uncertainties. But the first time we look at this planet with Webb, the demonstration we immediately confirmed that there is water in the atmosphere of this planet. So definitely this demonstrates that Webb is a perfect machine to try to understand the properties of planets, to identify planets that may be able to host life. And just to conclude, I want to show you these are simulations, but just to give you an idea of how we can use spectra to trace different molecules, different components, and also how we can use the spectra to understand the temperature and the surface gravity of different planets. This is a planet that is similar to the Earth. This is the atmosphere of a planet that is similar to Neptune, and it is a warmer temperature. And finally, this is what is called a hot Jupiter, a planet that is the size of Jupiter. It is close to its sun, and so its atmosphere is warmer than what we get for our own Jupiter. And you can see by comparing, by looking at how the spectra are changing, how we can really gather information not only on the chemical composition, but on the temperature and the surface gravity of planets of different size. And of course, the last thing that you've seen in last week is that we are going to use Webb to study also the solar system. This is an image of Jupiter, and we want to understand the atmosphere of Jupiter, but most of all, we want to understand the properties of the various moons that are around Jupiter, Neptune, and Saturn, because in some of these moons are extremely interesting, having some of them evidence for water vapors or having full oceans of methane. And so definitely these are extremely interesting targets that we want to analyze in details to see if there are other areas where there might be the development of life, maybe in simple forms, just small microorganism, but still they could be regions where life can develop. And I will stop here if there is any question. Oh, I forgot to translate this one. Sorry.
Great. Thank you so much, Elena. That is just incredible stuff to listen to. And I appreciate all of the animations and the analogies that you used, because this is really just groundbreaking stuff that you're sharing with us. All right, so I apologize again to our participants for having the chat feature disabled, but it does look like we have some comments coming through. Noah shares, this was awesome. Thank you for the wonderful presentation. Absolutely.
Noah.
Thanks, Noah. And if anyone has any questions, please feel free to use the Q&A function. We'll stick around for another 5 minutes or so. We'd love to hear any comments or questions that you have.
Too much information.
I have a question, Elena. I
Sure.
know that there are so many images, that the public hasn't seen yet. And actually, this is the same question I was about to ask that just came through. Michael asks, is there somewhere online where we can see the schedule of upcoming objects or observations planned for JWST?
Okay, so JWST is tweeting and it's telling you where it's observing right now. So you can follow that, and Hubble is doing the same. So you can use that. And then on the Space Telescope Science Institute website, there is the list of all the approved programs with the various targets that will be observed for the next year. Year and a half. And if you find a project that you're interested in, you can actually ask and see what is the schedule of that specific programs. We have a long-range plan that tells us roughly when we are going to observe an object through the years, and then we refine the plan about 3 weeks before, 2 weeks before we observe the target. It's really when we finalize what will be observed for 1 week, and then we send all the information to the telescope in periodically. But we adjust our observing plan in details on a weekly basis, because sometimes there are events that were not planned, like, I don't know, a very super cool AGN or supernova that explodes. We didn't know that it was going to explode, but of course we want to look at it with Webb, or we needed to adjust because there is a transit that occurs. Someone has a discovery and they ask to follow up with Webb. In general, however, we have a schedule that we adjust, also because sometimes observation takes a little bit longer and we need to readjust our plan because of that.
Right. That makes sense. Yeah, thank you for that question and for answering that. And Dylan and I both put it as an answer typed into that question, a link bank that we put together that has additional resources such as science briefings from the NASA's Universe of Learning, the James Webb Space Telescope webpage, where you can download the public domain images for free.
Yeah.
If anyone would like to use those in any of your library programs, or honestly, I'm kind of thinking about like printing some out on metal just to hang up in my house because they're just gorgeous. And especially getting some context about what is going on in those images is really great. But check out that link bank if anyone wants to find
any
more.
of the slides in this presentation also. So
yes, thank you. Yeah, we will be posting the slides and the recording on the StarNet website. So check that out. And there is a link to our webinar recordings on the link bank. Mary Ann Johnson says, thank you, Elena. That was fascinating.
I noticed a wobble in the animation of the orbit of the telescope. What is going on here? Is it remain of the shadow? Is there? Okay, so the telescope is orbiting with the Earth around the sun on a circle, but then the telescope also, I'm looking for the animation. But also the telescope needs to face the sun all the time to recharge its solar panels. If it was sitting exactly on L2, it would be constantly in the shadow of the Earth, and so it will run out of energy very, very soon. Instead, this way, by orbiting around the Earth, it can always face the sun with the solar panels. And as a result, the orbit is not just a circle, but it is a wobbling circle. That was a very good.
Yeah, great observation there, Noah.
Yes.
All right. Well, it is 2 o'clock, so that was perfect timing. Thank you so much, Elena. If anyone else has questions, our contact information is on that link bank, so feel free to reach out to us. But enjoy the rest of your day, everybody, and big thanks to Elena. Thank you so much.
Thank
Thank you so much, Elena. This was great.
Yeah,
thank
so
you
fantastic.
for joining me. Well, I'm glad you liked it, and yeah, if you have other questions, feel free. You can also send me an email, and I can answer that.
All right.
Okay.
All right. Well, have a great day, everybody. Goodbye.
Bye-bye. Thank you. Bye.